Okay, thank you for inviting me here. This is a bit different direction than what we have heard today, at least. Well, it's the same topic, but I'm in the other direction. I'm really doing the materials rather than the abstract theories. But I try to understand a little bit of what you're doing and then see how good I can perform in making materials for what you want to do. So I am actually hired in 3 different places at the moment. Hopefully not for too long, but I'm positioned at Niels Bohr Institute in Copenhagen, in Center for Quantum Devices, where Charlie Marcus is leading the center. And then I'm also just recently hired by Microsoft in their effort to build something interesting with topological qubits. And I'm actually both located in Copenhagen and Delft at the moment because they don't have a lot of material science people in Delft, so I'm flying back and forth each week. And yeah, we could need some people. If there's any material scientists in here, then please help out. So in the presentation here, I will show slides from where I need to acknowledge these people here. In Copenhagen, it's a bunch of students and some senior people here. You know probably many of them. Then we also collaborate with UCSB on a new direction which is called selected area growth, where we try to grow the nanowires in plane instead of the usual VLS growth and or 2DEX. So that's a third kind of approach we are starting up here and think this is maybe the most scalable approach we can think of. And I will talk a little bit about that as well. And then there is a TEM team in Barcelona we are collaborating with. Okay, first of all, I've been working a lot on making X's in situ because that was, at some point it was the hot thing to make X structures in situ, and so you can make coherent transport across junctions here and make braiding schemes. So we used a lot of effort on different approaches to make this happen. But then there comes another X, a bigger one, that say this doesn't work, or at least we don't want to go that direction. So now we're more into this kind of schemes where we can use single wires with some loops involved, and which also set some different challenges. But I think we are on a much easier track right now. Actually, this could also be a single wire, which I will not talk about, but where you can put, for example, code a hexagonal nanowire with aluminum on 2 sides, and then you have 2 channels if you deplete the middle section. This is also something we're working on. Okay, but we are primarily down to the quality of single wires now again. So that's a new focus here. So how do we make a Marana wire, a good quality Marana wire? So the main thing here is, the requirement is we want this spinless, one-dimensional nanowire as originate from Kitai's idea with the toy model of an electron chain. I don't know if it's a toy model, but it looks like that. But fortunately here later, much later, there was these papers which kind of proposed that this can be done in real materials, in scalable materials as well, in superconductor, semiconductor, and so forth. But of course, then we get a lot of material requirements, and we have to, in one nanowire, we have to really have a lot of requirements in order to go into this 1D spinless Marana wire. Of course, we need a strong spin-orbit coupling, large G factor to merge the states into 0, low effective mass. You can split the levels. Of course, these are typically semiconductor thing which goes together. So in indium arsenide, indium antimonide. We want high mobility and low disorder, of course. It needs to be superconducting as well. So all these is actually effective parameters I'm talking about. So it's a hybrid. I'm thinking about this material, which has where we want to get a little bit of one material, a little bit of other, and we have to put together to one wave function, which kind of have everything. We also need a low Krogstrup Poisson rate, which could mean maybe a hard, not even a hard gap, but also a wide gap. So it takes a lot of energy to excite an electron to a state that's somewhere above the gap. If we want to split the lift the degeneracy of the Zeeman field, then we need a high critical field, most likely, all the way up to where we reach the topological regime. Or maybe we can also use some other material that actually intrinsically splits the levels, like a ferromagnetic insulator, or maybe not insulator. It depends on what we do. So this is all a new field we are trying to look into, if we can kind of make a topological wire in one go. So you just give it, here you go, and don't need to do more. Another thing, it has to be gateable, and to go to the modes we want, and so on. There's a lot of requirements. So even though it's single wires, it's still complicated. Yeah, so the solution is to if we want all these things, we need to go to hybrid materials with low level of disorder. And the real solution is we have to grow these materials together in situ without exposing to air, where we get a lot of disorder when we need to remove the native oxide that builds up and impurities that builds up. If we can build everything in situ, that's definitely the way forward. And the way we do that, at least for the superconductor growth, is we can do in planar materials, of course. We have one option, and that's just deposit on a plane, which is good. And then you can cut out your patterns afterwards. In this sense, nanowire materials have more options, because you can put it on different facets. The different materials you want to work with, you can put it on different facets, and you just rotate it with respect to the sources you want. So, for example, if you know the crystal orientation of your wafer, and you know the orientation of your beam of atoms coming in, then you can orientate the wafer and you also know the faceting of your crystals, then you can put for example, your superconductor on 2 facets here, and all 3 facets and so on, and we can do like that, or we can even choose to put it on 2 facets here, 2 facets here, and a different material on these 2 facets, and so on. So that there is much more interesting things of degrees of freedom in making nanowires, but it's not, of course, as scalable. So I think Microsoft would like me to go to 2DEX and select the area growth at least, so they can build a quantum computer. Here is a nanowire with a full shell aluminum, and this was the first thing we tried when we grew these materials together. We will see we can proximatize superconductivity much better than we've seen before by just doing everything in situ and then etch away the aluminum where we want the junctions afterwards. And we didn't calculate the match before we did it, but it turned out to be a really beautiful match. This is relaxed structures, just giving the bulk lattice constants, and they really match up in all dimensions to one hybrid coherent crystal with a 3:2 ratio. That's just from a material science point of view, that's nice, but I don't know if it's important for what we're doing. You can also see here there's a cross section of the wire. It follows the facet of the wire in here, so it goes into the same overall crystal symmetries. Here is a close-up on the interface of this kind of nanowire, and if we try to simulate how they match up in this 3:2 ratio, and you look in normal on the interface, there's a very small interfacial domain, and it persists throughout the nanowire. So it's really, it has a low level of disorder along the interfaces. And this gives a hard gap. At least it looks like it's really found in one of the main sources for a soft gap. And we compared with the soft gap here from the conventional way we did it before. Okay. Yeah. Yeah. Okay, so you think because it's more transparent, then you will just see the aluminum gap if you make a tunnel spectroscopy. Sorry? Yeah. 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 Then you will not see the aluminum gap. Okay. But these experiments are at least done in the same way, approximately. Yeah, and we just coded it on. We try to clean it up afterwards in situ and then put in a HA machine and put aluminum around it. But okay. So at least this structure is not very useful because you cannot gate it, and it has too much aluminum to go to high fields if you want to Siemens split, and also aluminum has a pretty small gap, so it would be nice to have to widen this gap. One of the main arguments in the beginning, it's too small aluminum, so we have a lot of coarse particle poisoning. But when you go to thin aluminum phases, you actually overcome a lot of problems. You increase the gap, you still keep it hard in the nanowire, and you can gate it as well, so you can tune as you will, which I will say. It's a different kind of crystal symmetry now. Now it's surface-driven grain growth because it's 1-1-1 out of plane. When it's very thin, it's the surface, which wants to minimize the free energy. So it goes into 1-1 out of plane, but it's still very well defined. And this was even though it's a very recent paper, it was still some of the first experiments we did on these wires. And we really see a hard gap still. And as we can change, we put some side gates on here, and we can really change the chemical potential inside the gap here, and we can see these levels coming in as function of gate. And as we go up in magnetic field along the axis of the wire, then we can move them closer to zero energy. And we can eventually go to zero spice peaks, as Carsten is showing here. Okay, I also showed this one because it also shows that it's really it has a large. I think it seems like it has a large Raspberry spin orbit, and also a G factor. They move in quite fast, these Andreev bound states in the nanowire, and then they stick really at zero. So if it's Marana, I think it will require a large spin orbit coupling to really make them stick this early here. But as also have been discussed quite a bit here today is why don't we see a larger zero bias peak? And actually, when we did these experiments, we were not very interested in the height of the peak because we were not theoreticians. We were just thinking, whoa, this is fantastic. It looks like what you want to see. But then we just went back. I just put this slide in, actually, into the measurements and look some of the old data we had. And here's as function of B field, we see that we get something at zero energy again. And it's really, sorry for not having this very high up here. This is 1.4, and then we stick here, and then we turn a little bit around in gate, and we can see it goes almost to 2e squared over h. But it's this is 1.8, but it's approaching the right values. And what is really something we can see when we get a high zero bias peak, it's typically when we have something when the junction shows some quantized depth, and not typically where we form these unintentional dots, as we showed in the science paper, where we coupled the wire with the dot. When we just have some QBC kind of behavior, then we really get a high zero bias peak. So there might be something to understand there. Okay. So we're looking at these, how do we improve the junction of these, because we are really suffering with this etched junction, because they form these intentional dots, and they are kind of different in nature every time we make them, because it's come from this etching, uncontrolled etch, where we remove the aluminum. So one thing we could do is simply make the junctions in situ by kinking nanowires across each other. And then this one will shatter for the one below, and then the aluminum will come in and only hit on the wire where it's not shattered. And then you don't need to make the edge. And we didn't work much with this, but we can at least see that we get some really beautiful quantized conductance through the junctions here. This is the superconducting state. It goes almost to 4 e squared over h, like it's a degenerate Cooper pair transport. And then as we go up in field, this is a lot of different traces as we go up in field here. It splits this degeneracy and really goes into 2e, at least for some levels. Yeah, it's a Delft geometry, the old fashion. Where you use this junction here. This is only on one facet, so this is kinked nanowires in a different orientation. And then it's only on the top facet of the wire, but then it's in situ. You don't need to etch this way because it's already formed in situ. So you just have a native junction in the wire. So another thing by going thin on the aluminum faces, this, as we talked about, it increased the induced gap a lot. We can see, or it increases the gap of the aluminum, which then has an effect in the nanowire. And for a 7 nanometer thick aluminum face, it really starts to make the gap much wider. It goes up to 270 micro eV. And we still have a really strong superconductivity. It's like, the superconductivity gets stronger because actually the gap is a measure of, as I see it, what is the difference in free energy between the normal state and the superconducting state. So it just gets stronger and stronger, the superconducting, until probably at some point where this will turn around and go to 0. And that will be interesting to see where this happens. We can also see that if we have these coherence peaks we have, as we tune the gate, this is all 0 field. As we tune the gate, we can see that these coherence peaks with gate can be moved in very close to 0. And then we can maybe stay on one of these ones and start playing with the magnetic field. So that's just mean that many have. I heard a lot of arguments that we don't want it too right, the gap, because then it requires a larger G factor to go into 0. But we can also simply move them in with gate first, and then we work in from that point. Okay, so this is a recent growth we haven't measured on yet, but it's really a 4 nanometer thick aluminum face here, and it continues on 2 facets all the way along. So it will be interesting to see what we end up with here. If we are on top, we go over and we kill the superconductivity, or it really becomes superconducting. It's very well-defined structure. It's interesting. Another thing, maybe also if we go thin on aluminum, is that the wave function will maybe spend less time in the aluminum than in the semiconductor, because it's pushed. Of course, it's a very short wavelength, Fermi wavelength in the aluminum, but when it starts going down to these scales here, it might push naturally the wave function into the semiconductor more, which will give larger spin orbit and G factor, hopefully. Okay, then I change and try to go into involving ferromagnetic materials. And this is just preliminary results. We don't have measurements on them yet, so it's just crystal growth, but I think it looks quite interesting. But how do we put it on? We are debating that quite a bit. So that we could put it on the opposite side. So if the wave function lives in the whole structure here and it takes up some exchange field from the ferromagnetic insulator, for example, on this side, it might be a good choice. So it's really the proximity effect from the superconductor is just going through. Maybe we can use it as an intermediate layer between, like a tunnel barrier, if it's really an insulator. So we can use this to tune both the coupling between the semiconductor and superconductor, but also split the levels with the exchange field here. Or it could be some hybrid function or whatever. It's maybe a thing for you guys to figure out. There's some different candidates, not much until now, if we wanted insulating. But the motivation, we are trying with European sulfide first, and because it's nearly lattice matched to indium arsenide, it crystallizes in the rock salt structure. It has a resistivity which is much larger than indium arsenide nanowires. At least this is also for debate, because there are some papers that show that once you go below the Curie temperature, then the resistivity go dramatically down. It's also a question of if it's a defect or what it is. And also if it is a problem that you can have the wave function living in this material. Okay, the first two growth we are trying here, these two models here. We don't have a quantitative argument for trying to do that, but more like this will be well defined. We will get, if we see superconductivity in here, then okay, then the Cooper pairs can tunnel in through, or the superconductivity can proximatize through this insulating barrier. Here we definitely know that it should be proximatizing through on these facets, and so on. European sulfide oxidize a lot, so we also use the aluminum to protect the European sulfide. But we could put it on the opposite facet and passivate with some other material. That's not a problem. This is on nanowires first. And what is really striking here is that this European sulfide phase is really, is first of all monocrystalline, and it continues all the way along the nanowire without any phase shift or crystal orientation shift. And the aluminum is also mainly in the same crystal orientation as the European sulfide. And this is a 113 out of plane. And if we look more carefully on the match between the European sulfide and indium arsenide rear side structure, it's really matching up beautifully. I think, yeah, here. So in the rock salt structure, the planes of these planes, you can see there's planes right here. So that's parallel to these planes here. This is 113 out of plane. And if you go along this one and look at the lattice planes, it really match up with lattice less than 0.1%, which is almost below the uncertainty of what we know the bulk lattice constants are. So it's really a perfect match. Just showing some different, this is probably way too thick for the final application, but you can see that it forms really the same crystal structure. This is from 3 different places, and the rhodium sulfide is just continuing. I guess that's important for getting a uniform Majorana wire. We don't want a different effective exchange field, change of exchange field on the length of the nanowire. So I think the first results, crystal growth results at least, looks promising with this material. We also done it on 2-dimensional materials. And here is the cross-sectional TM of it. It looks also quite good. You have some small, what looks like a little bit of defects here, but same overall crystal phase, which match up with the indium arsenide rear side structure. We can go in and quantify the orientations of where the atoms are sitting in the interface here. And because this is a technique called high in the dark field STEM, we can actually the intensity for each atomic column here is a measure of how heavy the atom is. And then we can kind of make a good estimate of what kind of atoms are sitting on different positions here in the interface. So we can make a detailed study of the epitaxial match at the interface, which is also good, I guess, for if first principle calculations will be done on this interface here. Let's see here. Yeah, we took a look at these ones. This is, of course, could be something that will disturb the uniformity of the film. And we can see that we go zoom in on this region here, and we make a FFT, fast Fourier transform of crystal array here, and we have to remember this is a cross-sectional, which is maybe 50 nanometers thick. So it's an average of the atom position. So in here there will be some different crystal orientation here shortly, and we can kind of map them out by FFT, and then we can see that we have a 90 degrees rotation right in this plane here. So there's some close to the degeneracy of these nucleation of this phase in a different orientation. So to get rid of that, I think we need to go to higher temperatures, and but that's of course an ongoing process to understand how this. We can also make geometric phase analysis on the interface to understand exactly how the atoms are sitting in their equilibrium position in this interface here. So geometric phase analysis is kind of measure of the displacement field of the different atomic columns. And when there's a change in crystal structure, you get a change in the phase here and the color. And you can see this is out of plane direction. We have a strong change in the periodicity right in the interface here. And it's actually up to 10% compression, what we can see. It's also good for if we want to compare it with this detailed atomic calculations of the electronic properties. In plane, there's simply no dislocations at all, so it's completely coherent interface. Material science speaking. But we also see in the one-on-one direction, we see a change. So there's some slight rotation, which we can also see in the rotation maps here, just around here. This is not quantified yet how much that would be, but we are close to kind of actually characterizing the interface down to atomic position, so how the interface is relaxing. This is just to make sure that we are looking at the right atoms. It's an elemental EDX mapping to see the right measurements. On this same So what are the things we are, 5 minutes, okay, good. Just want to quickly show some preliminary ARPAS data we did at the synchrotron in Switzerland, in PSI. We took a pure indium arsenide substrate, and then an indium arsenide substrate would grow the rhodium sulfide on here. And first, of course, we get a very high intensity for the band structure in the pure indium arsenide case, when we don't have anything on top, because the mean free path of electrons, which is coming out of the sample in ARPAS experiments, is only a few nanometers maximum. So you can, even if you put 2 nanometers of rhodium sulfide on, then you cannot see anything below. But at least we tried anyway, and we see that there's a conduction band peak just right above here, well in the right at the gamma point here. So this is a good measure of the Fermi level, is what we think here. And then we probe the rhodium sulfide here, and they're very strong intensity here because it's right at the surface, of course. But we take away that surface, we can still see the bands of the indium arsenide below. And then we can kind of say what is the Fermi, what is the alignment between the indium arsenide and the rhodium sulfide. And looks like when we really make detailed characterization around the Fermi level in the rhodium sulfide, it looks like there's completely empty of carriers. It looks at 12 Kelvin, it looks at least not superconductive, I think we can conclude. Okay, I will finish up by talking a bit broad about our approaches. Main approaches, I've been talking quite a bit of VLS growth, where you grow bottom-up nanowires. This is maybe not the future. So we're also thinking about 2DECs as Carsten was showing here. This is actually when a 2DEC is perfect, then it looks like this. You have atomic steps separated by, in this case, 300 nanometers. This is really perfect material. But then we have this selected area growth effort, where you can actually, but the downside with the 2-dimensional materials is that you have to do everything top-down when you define your network. It's difficult to really scale up in that way. You need some really precise alignments and so on. So that's a different challenge than the nanowires. But with the selected area growth, if we get high mobility and get selected area growth nanowires to work, then of course everything is just intrinsically, you can just draw whatever you want. If I just start with the VLS, it's not like what we are doing now when we thinking about the approach we are doing now, this in the case of some of these funny structures there, is that we use a manual manipulator and then we kink them off, and then we can place them on the substrate like this. And this takes approximately 2 hours or something to put 6 wires on here. It's not a scalable solution. Of course, you can grow the whole network in one go like this, but that's also difficult to think how we actually going to use this network. Then there's maybe the most exciting or the most promising way to do it. If we want to use nanowires, is that we use dielectrophoresis. You can see here, this nanowire was use a solution with nanowires, and then you have some electrostatic potential across here. And then they simply just fix into the position. And, oops, maybe I make it large again. So this one here, this is some gap between these contacts here. And then you put electric field across. And then they come in, and then they snap in like that. And here is an example of the Transmon group in Copenhagen who used nanowires, used dielectrophoresis, and then you have these 6 different places where we want to position the nanowires, and then we just make this dielectrophoresis and they snap into the places. And it seems to work. All the devices here show coherence times around 1 microsecond up to 5 microseconds, and all of them work. So at least it's not completely. If it turns out that we have to live with nanowire, less nanowires, then it might be possible still. Okay, I'll just quickly finish off with selected area growth. There's some preliminary. You can see that's how quickly. Oh, we're not going to have to cover it. Whoops. Looks better. So this is a material indium arsenide nanowires grown on an indium phosphide, insulating indium phosphide substrate in a mask. And the way is that you have a beam of atoms coming in. In this case, it's a chemical beam epitaxy, where it's easiest to grow this kind of things if you want ultra-high vacuum at the same time. And when they meet this dielectric mask, they simply desorb or they dissociate, and then the growth species diffuse until they reach the crystalline substrate here. Then in this way, we can grow really well-defined nanowires. In this case, we'll make a small buffer, and we can grow them in the ways we want. We can also make a study of crystalline quality as function of direction. Of course, in the high symmetry directions, they are better than if you're off-cut. It looks terrible, but at least we can make networks that are all square. And it's very reproducible. So I'll finish here and say you can kind of build, if we get this to work, we can kind of build everything we want.